All right, a couple other just important ideas, some things that we touch on in this chapter. If you read the chapter, you'll find out, um, and they are important. All right, but they just kind of don't tie directly to what we've been doing quite as much. All right, so taking a quick look at some of these other things. One of the object or ideas is the fundamental theorem of calculus, but part one. We did the part two where we evaluate the definite integral, but part one is saying, or I guess talks about how derivatives and integrals are connected. Okay, so if we have a function and it's continuous, all right, and capital F is the antiderivative of lowercase f, then the idea is if I know this, capital F is the antiderivative of lowercase f, if I take the derivative of the antiderivative, all right, if I take the derivative of this, it basically cancels out the antiderivative part, the integral part, all right, and so we're just left with the function, okay? So the derivative of an integral cancels it out, okay? So if I have a function and it's given by this thing, notice my x is up here, but my t is in here, and I'm doing the integral with respect to t. But x, my variable, f of x is up here. All right, the general idea is if I do f prime, the derivative of an integral is going to cancel out, and so I'm just going to have this function, something squared plus 4, the square root of something squared plus 4, and my x is just going to become this something. Okay, so basically taking the derivative of an antiderivative, derivative of an integral, is going to just cancel out the integral symbols, all right? And our bound, whatever x value we have, is going to kind of replace whatever variable was in here, okay? So find g prime when g of r is this, okay? So g prime of r, the derivative of an integral, is going to cancel out my integral sign, and the r is going to replace that x. Okay, so overall, the idea pretty simple. The derivative cancels out the integral, all right, and we're left with just whatever new variable we have. All right, where this gets just a little bit harder is if it's not just a regular x, all right, when you have a square root or when you have an x squared. All right, so when we do a derivative, in this case, so we take the derivative, it's going to cancel out our integral. So we have sine of the square root of t, the square root of x, all right? So this goes in place of there. But remember when we were doing derivatives and the inside stuff is more than just, so the stuff inside of sine is more than just an x value. Remember doing the chain rule, all right? So we then have to chain on the derivative of the square root of x. So if you remember, square root of x is x to the 1/2. So 1/2 x to the negative 1/2. So we can simplify this up. It would be what? Sine of the square root of x over 2 square root of x. All right. So again, if we're taking the derivative of an integral, the derivative will cancel out the integral. This will replace this. But since the inside stuff is now more than just an x, we have to chain on its derivative and try to simplify. So what? 3 times 2 is 6. X squared squared is x to the 4th. And one more. So 6x to the 5th. All right, that's called the fundamental theorem of calculus part 1. It's very kind of important when we're thinking about how derivatives and integrals connect to each other, but it's just not something that we use all that often, okay? Rarely do we take the derivative of an antiderivative. We don't usually cancel out the work we're trying to do, okay? But it is there. It is something that exists. We really use that fundamental theorem of calculus part 2 when we evaluate these integrals.